This is Chemistry Made Simple YouTube channel. I take this opportunity to once again welcome you to another great learning segment. Today we complete our previous concept, and that is none other than the concept of isomerism in organic compound. Previously we have looked at the class of isomers that is generally known as constitutional isomers, and for that case constitutional isomerism. So let us finish it up all by looking at the second general class of isomers, and for that case isomerism, that is known as stereoisomers, or for that case stereoisomerism. Ladies and gentlemen, what is the meaning of stereoisomerism, or what is a stereoisomer? A simple definition is that stereoisomerism is the type of isomerism, or is the class of isomerism, in which isomers have the same molecular formula, the same structure formula, but differ in the three-dimensional arrangement of elements in space. Stereoisomerism is subdivided into two other types, and these are: number one, optical isomerism, which gives us optical isomers like we shall see, and number two, geometrical isomerism, which will give us geometrical isomers. Ladies and gentlemen, welcome to the first type of stereoisomerism, and that is optical isomerism. First things first, what is the meaning of optical isomerism? Optical isomerism is defined as the type of stereoisomerism in which isomers are plane mirror images of each other and are non-superimposable. We need to understand what it means by non-superimposable images, or for that case non-superimposable isomers. To illustrate the words non-superimposable, I will use the displayed number 5 here. Now if you look besides the two number 5s that have been displayed there, if you tried to move the two number 5s towards each other, it is possible that at some point the two number 5s will completely eclipse each other, such that each of them is exactly on top of the other as displayed, and in that case we shall say that you have managed to superimpose the two numbers. However, also displayed there are other two number 5s. Now the two displayed number 5s there can never superimpose each other. In other words, one can never completely flip over the other. Now in this case, these two number 5s, one of them is a typical plane mirror image of the other, and that is what we mean by optical isomerism, is that the two isomers are such that they are plane mirror images, number one, and number two, they are non-superimposable over each other, like we have seen in the second illustration with the two number 5s. For that case, therefore, for any organic molecule or any organic compound to be an optical isomer, it must possess at least a single carbon atom that is attached to 4 different groups. And mark the words at least, means it could be one or more than one carbon atom. Now this specific carbon atom that is attached to 4 different groups is generally known as a chiral center, and is referred to as the center of optical activity in an optical isomer. To illustrate the whole concept of optical isomerism, displayed besides here are the optical isomers that are associated with lactic acid, whose exact IUPAC name is 2-hydroxy propanoic acid. Now the two isomers are D, lactic acid, and L, lactic acid. Now kindly look at them and notice that however much you try to superimpose these two, you will never succeed without twisting one of them, and therefore they end up being perfect optical isomers. The second example also displayed there are the optical isomers in the amino acid alanine, whose exact IUPAC name is actually 2-amino-propanoic acid. Now, the two optical isomers generated are D-alanine and L-alanine. Notice that also, like in the previous example, however much you try to superimpose those two isomers, you'll never succeed without twisting any of them. And therefore, the two are a perfect example of optical isomerism, and for that case, optical isomers. Any one of the two optical isomers displayed in the above two examples is generally known as an enantiomer, and both of them are enantiomers. Due to organic synthesis, it is possible that you can end up producing a mixture of two enantiomers. In other words, a mixture of two optical isomers. Now, if that mixture contains 50% of each of the optical isomers, that is the D optical isomer 50% and the L optical isomer 50%, then such a mixture is known as a racemic mixture. Both the orange plant and the lemon plant may look the same. By this I mean the smell of their leaves is almost the same, and also the smell of the orange peel is almost identical to the smell of the lemon fruit peel. However, the two fruits are not the same. Now, the reason is simple. These two fruits, I mean the orange and the lemon, have peels that have exactly the same smell due to the fact that the two are optical isomers. In other words, inside the lemon fruit peel and also inside the orange fruit peel, you can be able to extract either by steam distillation or any other separation techniques a compound that is known as limonene. While in the orange, there is D-limonene. In the lemon fruit, there is L-limonene. A simple definition of geometric isomerism is geometric isomerism is a type of stereoisomerism in which isomers are not non-superimposable plane mirror images of each other. In other words, the whole concept of plane mirror superimposability is only restricted to optical isomers. Geometric isomers predominantly exist in alkenes and cyclic alkanes. Geometric isomers will depend on the arrangement of priority groups, either along the carbon-carbon double bond, that is for alkenes, or along the carbon-carbon plane in cyclic alkanes. Now, when priority groups are arranged or oriented on the same side of the carbon-carbon double bond, and for that case on the same side of the carbon-carbon plane in a cyclic alkane, then the geometric isomer that is obtained is known as the cis isomer. However, when the two priority groups are oriented oppositely along the carbon-carbon double bond or along the carbon-carbon plane, then the geometric isomer that is obtained is known as the trans isomer. To illustrate the words cis and trans, I have two examples here. The first example displayed besides here is derived from the alkene but2-ene. Now, on a close analysis is that the two methyl groups can be oriented on the same side of the carbon-carbon double bond, and therefore we obtain the cis isomer that has been named there as the cis-but2-ene. However, we can also have the two methyl groups oriented opposite each other across the carbon-carbon double bond, and therefore we obtain the trans isomer, and its name is trans-but2-ene. Point of emphasis here is that for an alkene, and for that case therefore a cyclic alkane, to exhibit what is known as geometric isomerism, then you must never have two similar groups attached to the same carbon atom. For example, to illustrate this, besides here is the compound that is 2-methyl-prop-1-ene. Now, notice that this compound can never exist as a geometric isomer. That means there is no trans isomer for this compound, neither is there a cis isomer for this compound. Reason being that there are two methyl groups on the same carbon atom. Our final example to illustrate geometric isomerism is displayed there, that is derived from the cyclic alkane, that is 1,3-dibromocyclohexane. Now notice that we can obtain two isomers. The first isomer, the two bromide atoms are oriented on the same side of the carbon-carbon plane, and therefore we obtain the isomer that is displayed there as cis-1,3-dibromocyclohexane. And also it is possible that the two bromide groups can be oriented in opposite direction of the plane, such that one is below the plane and the other is above the plane, as displayed besides there. And the isomer that will have been obtained in this case is trans-1,3-dibromocyclohexane. Ladies and gentlemen, this becomes the end of the concept of isomerism. Do you have any challenging concept as related to organic chemistry? Please contact me by sending me an email using the email in the description of this video, and I will humbly respond to you. Until next time, I remain yours, your chemistry teacher. Goodbye.